All right, let's get right into it. We're going to pull back the curtain on a really powerful, invisible force that's shaping just about everything around us. I'm talking massive bridges, all the way down to the jar of pickles in your fridge. Today, we are talking about the hidden force of thermal expansion.
You've seen this before, right? These little, deliberate gaps in these enormous structures. Kind of seems weird, but they're there for a super important reason. And by the end of this, you're going to know exactly what that is.
The answer to that little riddle, well, it lies in a really fundamental principle of physics. It's something that's happening all around us, every single day, whether we notice it or not.
And here it is. Thermal expansion. At its core, it's a pretty simple idea. When you heat things up, they get bigger. When you cool them down, they shrink. This affects solids, liquids, and gases. But for today, we're going to focus mostly on solids.
You know, to really get it, just picture the atoms and molecules inside an object as people in a big crowd. When everything's cool, they're all standing pretty still, not bothering anyone. But as you add heat, you're just pumping in energy, and they start to jiggle and dance, and they start pushing each other apart, demanding more space. That collective push, well, that's what we actually see as expansion.
So this growth, it isn't just random, it's actually really predictable. Physicists have broken it down into 3 distinct types, basically depending on which dimensions we're looking at. Let's check them out.
Okay, first up, we've got linear expansion. This is the simplest one to think about. Imagine a long, thin thing, like a wire, or hey, a train rail. When it heats up, the most obvious change is that it just gets longer. We measure how much it expands using a special number that scientists call alpha.
Next, picture a flat sheet of metal. When you heat that up, it doesn't just get longer, it gets wider too. Its entire surface area actually increases. This is called superficial expansion, and its coefficient is known as beta.
And finally, for a full-on 3-dimensional object, like a metal cube or maybe a ball bearing, everything expands. Its length, its width, and its height all increase. This change in the total volume, that's cubical expansion, and we represent it with the coefficient gamma. Now here's the part that's just so cool and elegant. It's how these 3 ideas all connect. For most materials, the coefficient for area, that's beta, is roughly twice the one for length, and the one for volume, gamma, is about 3 times the one for length. It's this beautiful, simple 1-2-3 relationship. So neat.
Okay, so that's the theory. But this is where it gets really fascinating. Because this isn't just some concept in a textbook, it's a powerful force that engineers have to deal with, and sometimes cleverly use, every single day.
So let's circle all the way back to our first question about those gaps in the railway tracks. Without that little bit of room to grow on a hot summer day, the immense, unstoppable force of that expanding steel would have nowhere to go, and the rails would bend, they'd buckle, and it would be a total disaster. That little gap is basically a safety valve.
But engineers don't just defend against expansion, they actually use it. Take riveting, right? A classic technique for joining steel plates on ships or bridges. You heat the rivets so it expands. You pop it into place, and then as it cools down, it shrinks, and that contraction pulls the metal plates together with incredible force, creating a super strong, incredibly tight joint.
You can actually see this whole principle in action just by looking up at the sky. On a hot summer day, all the telephone and power lines expand, and they sag down. You can really see it. But in the dead of winter, they contract, and they become tight and straight. Engineers have to calculate the perfect amount of slack to handle both of those extremes.
Here's another classic example. How in the world do you get a steel rim to fit perfectly onto a wooden wheel? Well, you heat the metal rim up. It expands, gets slightly larger, and you can just slip it right over the wood. Then, as it cools, it contracts and grips that wheel with enormous pressure, holding the whole thing together.
But sometimes, the whole goal is the exact opposite, to prevent expansion. The timing of a pendulum clock depends entirely on its length. So if the pendulum gets a little bit longer on a hot day, the clock actually runs slow. To solve this, high-precision clocks use a special alloy called invar, which basically barely expands or contracts at all. This keeps the time accurate no matter the temperature.
But listen, you don't need to be a bridge builder or a clockmaker to see this force at work. It is happening right in your own home, probably most often in the kitchen.
Just think about these common situations. A glass stopper that just will not budge, a metal lid that's screwed on way too tight, or that heart-stopping sound of a glass cracking. Yep, all of these are governed by thermal expansion.
Here's exactly what's going on with that glass tumbler. When you pour hot water in, the inside layer of the glass heats up, and it tries to expand instantly.
But glass is a pretty bad conductor of heat, so the outside layer is still cool. It hasn't expanded yet. This difference creates this massive internal stress, and crack. There it goes.
And now for your official physics-based life hack. That impossibly tight metal lid on a glass jar, just run it under some hot water for a few seconds. The metal lid heats up faster and it expands more than the glass jar does. This loosens its grip just enough for you to twist it right open. You're literally using thermal expansion to your advantage.
So there you have it. From railroad tracks to a stubborn jam jar, thermal expansion is this constant, powerful force. It's a perfect reminder that our world is governed by these elegant, unseen principles. The real question is, now that you can see this one, what other invisible forces are out there shaping the world right in front of you?